Hello everyone, I am Dr. Gaurav Chaparwal, COO at Paanduv Applications. In this session, I will show you my expertise in simulation of laser powder bed fusion, in short LPBF process. We will use PravaH software, which is flagship product of the Paanduv application, and we will see in-depth analysis of melt pool evolution. This is the flow of the session. First, we will have the introduction to the AM. Then we will reach to the problem statement and objectives, numerical setup, and then we will have a trial simulation to declutter the unnecessary which are not possible in this time constraint. So that parameter we will narrow down, and then we will have validation with PravaH, where we will do the setup and in-depth analysis of the melt pool dynamics. Then conclusion and assignment also will be shared after this session that I will recommend you to practice at home to explore the capabilities and features of the PravaH. So before we jump into the additive manufacturing, I strongly believe that all the scientific research or the inventions have deep inspiration from the nature, and AM is not an exception. Here, a spider makes a web to trap the food or the prey. And these are the mollusks like snails, oysters that deposit calcium carbonate over their body for the protection. Honeybees makes perfectly hexagonal structure to storage the honey and as well as to lay the eggs. Here, these tiny creatures and birds make their home by adding layer by layer the material, and termites and ants can make the whole city. And the word also, the corals deposit calcium carbonate to make the reef. That's also sort of additive manufacturing in nature. Yeah, many of you might not agree with this, but yeah, the stars, our mighty existence, the universe, all the physical objects in the spatial place are formed by the continuous accumulation of the dust particles, gases under the force of gravitation. And thereafter, the planets are formed around it. Now, from the billion light years of time and space, let's come to our survival dimension, the AM, the additive manufacturing. So we have to narrow down the whole possible areas of studies. Like there are 7 different AM processes according to ASTM. Out of that, we will study LPBF. And there are many application areas like aerospace, automotive, medical. We will deal about the aerospace. And further, there are in the LPBF itself, there are many parameters like the laser parameters, thermal properties, and fluid properties, convection, powder material properties. There are total 50 plus parameters that we can study. Out of that, in this session, we will deal with the laser speed and scan speed. And there are number of alloys, like 10, around 10 plus alloys are there in aerospace. Those are used to manufacture different parts of the or the technology in the aerospace. Out of that, we will study Inconel 718, and in that we can study like the melt pool dynamics, microstructure, and structural analysis also. So here the session will be about the melt pool. So when we have narrow down all the parameters, now we are in position to define our problem statement. So before we define the problem statement, let's have a brief introduction about the additive manufacturing. It's a type of manufacturing technique where we develop a product by adding layer by layer, and it has vast applications, almost penetrating into almost every domain. Now LPBF. So here is the schematic diagram where we have the powder bed on which the metal powder is filled. Then we have a substrate here, of which laser provides the heat source to melt this metal powder, and time after time, the further metal powder supply is done by the roller or slider over it. And if we run the simulation, so this kind of uh, a process will happen where the laser falls over the metal powder and it melts it, and according to the scan speed, it will move further and make a single layer. It can be single layer, multi-layer, multi-track. Later, after solidification, we can study the microstructure also. So microstructure will be dealt in the next session. Now the aerospace materials. So these are few commonly used aerospace materials. And in Conal 718, which has high strength, corrosion, and temperature resistance, which make it suitable to make the gas turbine blades, disc, and other high temperature components. Now, before we move to the simulation, one question arises in the mind: why we need the simulation? First of all, the experiments that are conducted in this domain are very expensive. The metal 3D printer use is also expensive. So it will reduce the testing cost. It will predict the part behavior, optimize the design, and that will ensure the safety in the areas where it is very critical. Now, the problem statement. So in LPBF of Inconel 718, we are trying to predict the melt pool geometry and defects, which is quite difficult to study due to complex interaction and multi-physics involved. Experiments are costly, so validated simulations are essential or recommended for selecting safe process parameters. Now, to tackle the problem statement, we can develop certain objectives. The first one is the analyze melt pool geometry, which means the width, depth, and area. By changing the process parameters like laser power and scan speed, we can identify the defects, correlate it with the process parameters. Use high fidelity simulation to replicate the melt pool behavior, where the Marangoni convection and thermal distribution will be studied. And finally, we will validate our model using the experimental melt pool measurements. So this is very interesting part. Most of the time, we take these fundamental equations, which simulate the physics of the any physical phenomena, very granted. But we will try to go in each and every term here in best possible depth. First, the mass conservation. So obviously, the mass will be conserved until unless like it is not converting into energy, which is not the situation here. So mass will be conserved. So obviously, mass conservation equation will come here, and then and it's an incompressible flow, which means the density is not changing. So we are not taking the density term here. So it's only the velocity is coming in. The second is the momentum equation. Now, in the momentum equation, first of all, why the momentum equation will come? Do we have the fluid here? Yes, of course. First, the fluid that is the molten metal that is formed due to heat source provided by the laser. That is the first fluid. Then the vapor will be also formed during the melting process, and that will be the another fluid. And the third one is the shielding gas that will flow from one part of uh, the metal or the chamber and will pass out from the another side, which will help in protecting this the whole process and take out all the unwanted byproducts as well as cool the this substrate and the powder area. Now, what terms will come here? First of all, so momentum is changing in 4 dimensions. The first one is the time, and the second and the other are the XYZ directions. Now, here it is changing because of certain forces which are acting on this whole phenomena. So we have to find out those forces. So whenever there is a fluid flow, obviously the pressure will be there. That is, fluid always flow due to change in pressure. And pressure has the same importance that the temperature have in the fluid flow. But what about the others? So the others is the viscosity. So whenever fluid will flow, if it has viscosity, there will be a viscous force. So these two terms are quite obvious and will be there. The remaining two terms that we need to find out after carefully study of the whole process. So the melt pool which is formed here will have liquid or the molten metal, and that molten metal will have certain density, and the molten metal will have the temperature gradient also. So due to that, there will be a buoyant force. Apart from that, if we have seen the molten metal and we know that this the laser scanning is going from one direction to another or one place to another, it means that the previous part will have slightly less temperature than the currently melting powder. So that will make a surface tension gradient. So that will also push or create a momentum gradient. Now, now the density, obviously there is a phase change. So density and viscosity will be function of the fraction coefficient. Means some part of the molten of the powder will convert into molten metals, and there will be two phases of it. So accordingly, the effective density and effective viscosity will be there. Now, I'm sure that most of you know about it. Like what is this gradient term or the divergence we call it sometimes. So just for the sake of information, if we say uh, this del T, that means how the temperature is changing with respect to the x, y, and z. And if you put with the velocity, and then we will say that, like, because the velocity has three uh, vectors ux, uy, and uz, and how the ux is changing in x direction and uh, y component in the y direction and z component in the z direction. And now obviously the laser is providing the heat, so there will be energy equation involved. Now again, the velocity here was changing, here the temperature will change. Again, just similar to the momentum equation, the temperature will change according to time and according to the space. So what are the tractions that are making it change? The if there is a heat source, then obviously there will be uh, the transfer of that heat source into three possible uh, basic heat transfer mode, like the conduction, convection, and radiation. So that will be there. Apart from that, when we study this phenomena, then we will see that the phase change is also taking place here. So certain part of the heat will go into the phase change. And from where this the heat will come, it will come from the laser. So this is the heat source, which is going into the radiation, and it is going into the conduction, and here it is a convection. Now we are ready to run a trial simulation after the study of these fundamental equations and this multi-phase and phase change and laser reflection model, which are the I must say the most interesting part of altitude dynamics, will be covered when we will create the melt pool in the case study that we will have in the part 2 of this session. So that there we will discuss this so that we can easily correlate at the same time we are simulating it. So these are the process parameters. So I hope you all have installed the AM PravaH. So the first step, obviously, you have to click the AM PravaH icon. So first click on this home icon, and by default it opens in the home page only. There in the first button, you will see the project name that you can provide. So let's name it trial 01. Either use the single word, or if you want to use multiple words, use a underscore. Then create new. Although you can save it in any place, so I will just save it in the document. And I hope that you are following the steps. And just let me know if you are lag behind. Okay. So after that, we have these multiple options. So since we are studying the macro scale LPBF, we will click on here. Now, all these options are opened here. The first one is the material. So in the material, we will see that there are many alloys, and you can even create your new alloy also. Now, since I have already made trial 1, so let's make it trial 2. Doesn't matter. Then create new. And in create new, you will a choose directory option will pop up here, and there you can just save it anywhere. So I will just save it in the document section and click on the OK button. Okay. So now we have these options, and since we are dealing with the macro scale LPBF, we will click on it. And when you click on it, this interface will open. The first option is the material. So in the material, if you drop it down, then we have different alloys, and you can create even a new alloy also by putting all the values that you have with you. So we will go with Inconel 718. So you can see that if I click on the Inconel 625, the properties are changing. So let's go with the 718. Now we have the solid, molten, vapor, and gases. Solid is the when the powder is in the solid phase, and when it is in the molten phase, how it is changing, and when it is in the vapor or the vapor is formed, what are their properties, and the gas properties are there. Now the first one is the molecular weight, and second is the density. So the density changes with the temperature, although the variation is very less, and that's why we are taking it as an incompressible flow. And although for the solid part, the density is always very, the change is very less. Then we have the specific heat. Specific heat is also is considered as a variation or varying with the temperature. So it has values with different values. Then we have thermal conductivity, that is also changing. And then we have the latent heat of fusion. So what is the latent heat of fusion? So when a material changes from one state to another, and here it is changing from solid to liquid, then it absorbs certain heat, and the temperature doesn't change there. So that heat is called as the latent heat of fusion. And then we have the absorption coefficient. What is that, and why it's so high? So in the solid phase, the metal powder has very less transparency. So the laser is very hard to penetrate. And then we have emissivity, and this Lee constant is there for solid to liquid and liquid to solid, and then liquid to vapor. Lee constant, Fresnel coefficient, Marangoni effect, phase change, all these concepts and terms will be dealt in depth in the second part. So we will just move to the molten part here. So same thing is happening with the molten part, and it's changing with the temperature here again. But yeah, that variation is not too high, and that's why the incompressible flow has been taken. Then specific heat, dynamic viscosity, thermal conductivity, the same thing. Then the vapor part, we have specific heat, dynamic viscosity, thermal conductivity, and heat of vaporization. So that is also the same thing. This is also the latent heat, where the temperature will not change. And the vaporization temperature is by default is taken as 3000, and you can change it as per your requirement. But this will be the property of the material. So uh, you have to provide it as per the material you have with you. And the same goes for the shielding gas. Molecular weight, specific heat, dynamic viscosity, Prandtl number. Prandtl number is the ratio of momentum diffusion versus the thermal diffusion. So here the both are taking place. That's why the Prandtl number will come here, because there is a flow of the material, flow of the gas, all are taking the heat from one place to another. So there is a thermal diffusion also. Then we have the density. Okay. Now these are the shielding gas. So I'm taking argon here, and vaporization, I will own it here. Vaporization makes the simulation quite complex but realistic. So we will keep it on, and after that we will save it. After saving these options, this is a very important stage, because you have to go back. So after saving all the details, just click on the back, and then you will come here in the process. So I hope all of you are again in the same page. Now we will go with the process part. So material is done. We have set the material properties. Now we will set the process parameters. What are the process parameters? There are certain movements. First movement is of the laser. Second movement is of the powder bed. And third is the chamber where the gas is flowing. So all these movements, all this process will be defined here. So first go with the laser properties. So the first option is the scanning pattern. So how the laser is moving, that that is given here, that is feeded here. So when you click on the upload scanning pattern, so this is the trial 2 folders which are made while you have created a new trial case. So there we have dataset folder, and when you double click on it, you will see the particle distribution CSV file, the pattern CSV file. So here we will choose the pattern CSV. Now the scanning pattern has been uploaded. So I just want to show you what is there in the pattern CSV file. Here we have the coordinates and the time and whether the laser is on or off. So initially the laser is at the coordinate 0, 0, 0, XYZ. Then in X direction it moves this much distance, in Y direction it moves this much distance. In Z direction it is not moving. And then at that time it was in the on condition. Later it will move in the X direction and Y direction, but in the off condition to provide it cooling so that the laser can be cooled off. Now we have the laser beam types. So Gaussian laser is the most commonly used, or the laser have in its natural form this type of laser beam. So we will select it, and now we will give the components of it in the X, Y, and Z directions. So in the X direction, it's 0, Y direction 0. It's in the minus Z direction, -1 Z direction, because it's coming from top to down. So it's -1. Then the power. So this is the power of the laser. And then we have this spot diameter. What is that? So this is the area, the diameter of the area, obviously the circle, which have around 80% of the energy accumulated in that area. So that diameter is the spot diameter of the laser. So all these properties are for the laser. Then we have the Fresnel coefficient. For the time instant, just understand that it decides how the laser will interact on different interfaces, like the solid liquid interface, which is there, the liquid and gas interface is there, and then the liquid and vapor interface is there, and the solid and gas interface is there. So that will be again discussed when we will make or we will simulate a melt pool. There I will show you that how it plays an important role in simulating a very the right keyhole, and how the laser beams are or undergoes to the multiple reflections to trap the energy and create the vapor. So that will be done there in the second part of it. Then we have the powder bed preparation. In the powder bed preparation, we can select the particle distribution CSV file. So double click on it and it will be uploaded here. So let's see what is there in the particle distribution. These are the metal powder particles. So here is the size. Obviously it's a sphere, so it's a radius. And this is the concentration. So it's a 10% powder particles are of this size, 15% are of this size, 25% are of this size, like that. So this is the particle size distribution. Now the sphericity. Sphericity means if it is 1, then it is perfectly sphere. If it is zero point 0.9, then it is very close to the sphere but not a sphere. And it is defined as the surface area of sphere divided by the surface area of the particles. So if it is close to the surface area of sphere, then it will be 1. Then we have the standard deviation in the sphericity. Obviously, the all particles will not be of the same shape, and they will vary in the sphericity. So what is that deviation? If it is 0.1 and we click on the generate sphericity distribution, then it will generate it like this, because there were 10 different types of particles, so they have this kind of sphericity distribution. But we will keep it 0, so we will keep it that it is perfectly sphere. Keep it 1. Then the spreader clearance. So spreader, we have seen in our presentation that there was a roller, or we can call it a spreader also, which spread the powder, metal powder, over the substrate. So how much it should be above the substrate level, or the previously formed layer. So that will decide the thickness of the layer that is formed, then its velocity, and then we come to the chamber conditions. So preheat temperature is given. Why preheating is required? So that there can be minimal possible residual stresses and the product that will be formed will be machinable. Then the chamber pressure, which is almost atmospheric pressure. Then shielding gas velocity, gas flow angle, means at what angle from the horizontal it is input in the gas in this chamber. Then we have the initial substrate height, and then the substrate clearance at the boundary. So what is that? So we have the substrate. Substrate can be of the same material as the metal powder or can be different one, but they should have a good compatibility so that there can be minimum deformation and defects in the final product, and it helps in the cooling also. So it should be of best possible thermal conductivity. So that substrate that we simulate here may not be sufficient to keep the molten metal over its surface, but at the same time we don't want to increase our computational domain. So what we can do is we can give certain clearance in the all four sides of it. So that's the substrate clearance. And obviously when we are hypothetically providing a clearance at the boundaries, then we have to give certain thermal gradient also, because it is made of metal and metal will have the thermal gradients as the heat is or heat transfer is taking place through it. So number of scan layer is 1, and so just save it, don't forget to save it. Although we have not changed anything, we have just taken the default parameters. After save, go on the back side. Now we have set up our material properties, process parameters. Now let's go into the simulation control. So the first option is the accuracy. So what is that accuracy? Accuracy and performance are reciprocal to each other, and they have been calibrated in such a way that if we increase the accuracy, that means the mesh size will reduce and more better result will be simulated. If we keep or if we reduce it, then the coarse mesh will generate it and the results will not be good. So you can keep it 50, but just a trial run and we want to run it fast, so we will keep it around, let's say 10 or 15. In the performance, so that's can be linked with the performance of your systems, like it will perform fast or slow. Obviously if you make a fine mesh, then it will perform slowly. So the performance also we can increase. So very coarse grain will or the mesh will be formed here. And then we have the data saving frequency. Data saving frequency means it is also calculated like that. If you increase it, so more frequently the data will saved. If you reduce it, then the less frequently the data will save. So whenever we are creating animations, there it helps a lot. And also you can write or customize it in the seconds. And there is one important parameter here, the current number. So what is the current number? The computational domain that you see have certain cells. So we have mesh and data is transferring from one cell to another cell. And if the time step is not sufficient to capture that change, that then it will skip certain information, and that will accumulate it over the entire computational domain, and that will result in the bad results. So by default, it should be kept less than 1. Obviously, if you increase the time or decrease the time steps, then the computational power congestion will be high. the computational time will be high. But to keep it uh, to keep it in the accuracy in the range, you have to keep it less than 1. Then these are the physical CPU processor that it capture from your system. So maximum it can be 12. By default, 4 are given here. So you may have 8, 6. So according to your system, just keep it as much as high possible so that you can run the simulation in a minimum possible time. Then the subtrate that I discussed in the process parameter, which was given clearance, that is the thermal gradient that I discussed there will be provided here. So just save this the simulation parameters that will control the simulation, and then go back. Okay, हो गया ना? Okay, so we have set up the material, process parameter, and simulation parameters. Now after that, save all so that they should be saved in the sequence, which is quite important here. So this is the mesh size, this is the current number, and this is the maximum time step according to the current number. And the domains decomposition, which means how the computational domain is distributed or divided in X, Y, Z directions. So if you multiply it, then you will get the 8. So 8 cores we have used. Now we are ready to run the solver. So it is generating the mesh. And first, the powder will be spread over the substrate, and then the CFD will come, and the laser heat source will be provided, and the molten metal will be formed. So it will happen in sequence. So let's keep it running. Let me come to my presentation here. So in the objective, uh, that we will analyze the multiple geometry, and then we will correlate the defect with the parameters variation that we have done here. What are those parameters that we are not taken? We have taken the default parameters, but in the next validation model or the validation study, we will change it. So here, the momentum equation, we have seen the surface tension that we have provided, and in the energy equations, phase change was there, radiation properties were there, laser properties were there, and this is the Lee constant that we will discuss. So let's see the powder spreading. So the simulation is going on, so it will take a time, but we can see that the this spreader is spreading the powder over this substrate. So this is substrate. So if we go in the latest possible time step that has been simulated, so it's here. Okay, so this process has been completed. Now we can go into the show results. And here we have macro scale form. So this is the whole boundary or computational domain, which include the substrate as well as the powder as well as the vapor that is formed. So this is the solid part and this is the liquid part. So this is the molten metal. So this much metal has been, this much metal powder has been melted.
Hello.
Yes,
Sir, I'm getting error index list out of range.
index list out of range.
Ji.
So that we can discuss after the session in the support. Okay, so you can see here, this is the melt pool formed here having certain temperature range, and obviously it's not correct because we have taken the mesh size or mesh size very coarse. So and then we can see the velocity also. So in the center part, it is having the highest temperature. So obviously in the viscosity will be less. So more velocity will be there. And Same can be said for the solid part. So this is how the temperature is varying for the solid part. Okay. So you can we can do certain kind of clip formation here also to see what's going on the cross section. So just here in the I think it's on the fourth line there is a contour, then we have the clip. So click on it, and clip means it will just dissect it. And when you click on it, just unselect the invert option and then apply it. Okay, so we have by default in the X direction, we want it in the Y direction. So we can take just select this Y normal. So it will be formed here. So this is the clip form. So from there we can select the temperature, and we can show the mesh also here. So it's quite coarse, but yeah, we got the result on time. The same way we can unselect this and select the solid part, and again make a clip for it, unselect the invert and then the Y normal, and then apply it. Okay, we got it. Just change this pressure and make it temperature, and now you can see that how the temperature is changing in the melt pool. So it is having higher highest at the top where the laser beam have maximum possible heat source, and this is how the mesh. It's quite coarse. Okay, so just set it in the plus Y direction. Plus Y direction means, see in the coordinate system, if you put it in the plus Y direction, that means that it will come, the plus Y will come out of uh, uh, it will be in the plus Y direction. So that is the best suitable view. And let's make it in the minus Z direction so that we can see the top view. And we can create an animation for it also. So let's make it melt pool, the file types. Let's make it OGB, and let's make it 5 frame rate. Okay, if we go in the folder where we have saved our data in the document, there it was trial 2. So we have Okay, so this is it. Now in the part 2 of this session, we will take all these parameters and we will change the scan speed and laser power.
Can you go to the slideshow, please? It's very small. Yeah.
We will change the laser power and the scan speed. So that will be case 1, and case 2 will change it to the 1.2 370, and then case 3 will be different. The case, and then there we will discuss like important concepts like how the region is solidified and this Marangoni effect due to surface tension gradient and the phase change. Okay, so these are total 4 cases. These are total 4 cases, and so in the assignment, you can we will provide you the 3 cases with all the geometry, all the process parameters, and in tomorrow session we will develop this keyhole from the scratch. We will take the given parameters and then we will see how it is formed, and the case file has been already given to you, and that you can run, and I hope that you will come tomorrow with the case that has been already run, and we will discuss directly the physics of it in the parable. Okay, thank you very much. So I'm Dr. Gaurav Chapraval, CEO at the Paanduv application. I have done PhD in mechanical engineering and thermal fluid were my expertise, and that time searching in the additive manufacturing part also. Lots of heat transfer and fluid dynamics concepts are there. So yesterday we have formulated a problem statement where we were trying to predict the melt pool dynamics, the geometry, and we discussed that experiments are costly, although not replaceable, but can be supported with the help of simulations. So these were our objectives, and these were the physics of the melt pool dynamics, and this is what we are going to discuss today. And yesterday after the session, I have given assignment, and in those assignment these values were given. So, and the case study also given, like I think with the assignment, I think 2 days back we have given that case study. In that case study you can put these values, and then the accuracy is also given, at what accuracy you have to run it, and if you have run it, it would have taken couple of hours, and depending on the number of cores available in your system. And after the successful run of the simulation, we will be here with the post processing part. So let's start with the post processing part, and this will be hands on for you only and only if you have run that simulation, because it was high fidelity simulation and it takes number of hours. That's why all the details case files were given in the advance, and it was expected that you would have run it in the at the home. So just let me take the recap of the problem. So we were trying to simulate the Inconel's 718 metal powder, which is used for the aerospace application, and this is the laser power that we will take here. and the scan speed. Now, laser power and scan speed. See, if you increase the laser power, the heat source will increase. If you in decrease the scan speed, means it's moving very slowly, the laser, so then also the heat source will be more concentrated at one point, one location. So that will also contribute to the more heat source. So both are like, if one is increasing, the heat source is increasing, one is decreasing, then the heat source is increasing. So we have to take the optimum trade-off between both parameters so that we can get our optimal build. Build is the part that is made after doing this laser powder bed fusion. So we have taken spherical metal powder, and this is the particle size distribution, and this is the spot diameter, and this was a layer thickness, substrate height, chamber pressure, preheat temperature, Fresnel coefficient, and then absorption coefficient. Okay. So after taking all these values, we run the simulation, and after a couple of hours you will get your results, and the results will look like this, right? Yeah. So that we need to discuss here, means we need to make the mat pool width will be get 158 micrometer, and depth will be 138, and these are the experimental values that we have got from the research publication. Now we will try to replicate these results. So first of all, the step one, open the PravaH. When you open the PravaH, you can minimize this window, and then step two is load the project. So wherever in your system you have saved your run case file, you have to go there. In my system, it is on in the downloads. There, I have saved it with the folder name inc718 run, and there I will get this .PravaH extension file. So that you need to open. So step two is complete here. Now go into the macro scale LPBF, because we are doing this part only. Now you will see that the project has been loaded successfully from this location, right? So your step two is finally complete. Now all these values we have already given, so we will not discuss it. Process parameters already given, simulation parameters. This time, yesterday we have run it at around, I think, 15 accuracy. So that's why it was like it run very easily in a less time, and the performance was also very high. But to get the good results, you should keep accuracy as high as possible as per the technical specifications you have in your system. Now, first in the step third, let's see how to check the powder spreading. So it will take certain time to load the data, and now you can see that here we have this blockade. You can little zoom it also and rotate it to take the entire view. And now we have the spreader, we have blockade and the substrate and the another blockade. So this spreader, and here we see the time. So currently we are at the 0 time. So everything is just about to start. The powder is here, spreader is here. Now if we move with the time, and since it will take like a lot of time to spread the powder, I will directly go on to the 50 time step, and let's see what happens. Okay, so some of the powder has been already started spreading over the black blockade, and some is over the substrate also. Let's take it 100 time step. Just be patient, like it according to your the computing power you have with your system, it will might take longer time. So now nothing much is happening. Let's take it 150 now. Okay, so spread is over the substrate, and now you can see that. And don't zoom it too much, like if you don't have that much computing power with you, so because this PravaH can crash or hang. Now make it 175. Okay, so it's moving. Now let's take the final time step. So it is finally successfully spreaded over the substrate. Okay, that's all for this one part. Now go to your PravaH again, and there, after show powder spreading, now you need to go to the show results. Minimize this window. Okay. Now let's go to our PPT. So here we want to see the front view and the front view for the whole part, and then with the build part. So let's recreate it. For that, so you have these number of views here. So go in the plus Y set direction. Okay. Now okay. So now we can select the white normal plane, and there we can apply. We can remove this show plane because it will just crowd the view, and then apply. And now you can rotate it, and you can see it. Okay, we forget to unselect the invert button. So now the front part will be visible. So this is how it is looking. Okay, so the pressure is given, which is not important here. So let's take the temperature. So we can see that very high temperature is here. So this is the starting of the melt pool formation. So temperature is from like 373, that is the room temperature, to 3746. At certain points, not all points, the highest temperature will be found. And yeah, so now Now let's see the access grid, right? So for that, go into the ray tracing part, and there you have data access grid, and there you have the access grid. So select this access grid, and in the edit button, okay, after selecting the access grid edit button, you have to select this one, the back face, curl back face, and then the setting part, you will have to select the show grid and apply, and then you will get the proper grid here. Okay, so the build part also you can see here. Okay, so that's from here, the build part and the solid part you can both put together. And if you want to, if you just opaque, increase opacity, you can see the both parts, the build part as well as the solid part. And if you are seeing certain kind of partition here, and these are nothing but the because the solver was like running on the number of cores, so it divides the whole computational domain in certain numbers for the easy solving. Okay, so now come to the second view. Okay, so we can measure the width and depth also, which is quite important here. So let's deselect this solid and take the build and take the Y direction and make it 2D. Okay, from 3D we have to make it 2D so that it will not move, because it's very important that dimensions are taken very carefully. It should not rotate in any direction. So just make it 2D. Here the 2D is written over here. Now we want to, in this position, uh, you can take this position or minus that position. We can start with the width part first. So this is the build that has been formed over the powder bed. So now it's a little bit of subjective, but yeah, we can see we cannot take the width here, because here just the melting started, and obviously the simulation takes time to get established. And now, so just somewhere between like where the width started getting little bit stable, that point we can take, and that point we can take is like 0.0028. So that value you can take. And now be careful this part, like and just go with me. Now we want to calculate this distance. So from this point to this point, so width we are going to take. So take the width, we will just go into the ruler. Okay, just go into the ruler. So that there you have to select the point. And now this is very important. Take your mouse and click on the left button, the left button, click one time and then press 1. Okay, again take the mouse exactly in the perpendicular direction and again click left button of your mouse and then the press 2. Okay, and then apply. It will take certain time. Just wait for it. So post-processing part is very heavy. It's required the graphic card and other computing power. So just be patient with it. Then we can, I think, force kill it. We can force create it, and then let me run it from the start. Third. Pick the build part. Take the final time. Remove this window. Okay, and minus add, make it 2D. And take the ruler. Now I think it's perfectly working. Now you can take without the grid lines also. Just left button of the mouse. Wait, getting again. Okay, so let's do it again. Uh, then take the final step. Let's take the grid lines. Show the grid. I. Okay, and take it here and take the rule. Uh, from here also, if you just go here, 0.003 to here. So it's so you can take it like you have to do some manual calculation here. Uh, go up to the 0.003 and we can see that it's around 70 or 60 around, and then it's 70 at the top or around 80 at the top. Okay, so that means it will come around 130 or 130 or 140. Okay, So let's come into the visualization of the Marangoni flow. Yeah.
Hello, sir.
Yeah.
Sir, can you please repeat that grid part?
Okay. Go into the grid part. So make it 2D. Make it axis the axis grid. So here, just take it like it is getting stable here. That is around 80, and at the top it is around the 80. So
Sir, when I'm doing axis grid, I can
mhm.
see the grid point, but I can't see the values.
So you have to zoom it. The values means on the grid part. Which values? Like these scale values.
Yes, sir, scale values.
Have you selected this axis grid?
Yes, sir.
Then it should show. Or means you are not getting these fine values, right? So for
Yes,
that
sir. I can see the lines, but not values.
so you have to zoom it. And have you select the build also? Have you selected the build part?
Yes, sir. Only build and logo one were selected, but I think
And
you
then
have done
select,
so.
yeah, select the edit, and then this curl back face, and in the setting, select the show grid,
Okay, sir. Okay, okay.
and curl back face will bring your grids on the front side. Okay. Now let's go for the Marangoni part, and just take the build part. Okay. Go into the liquid part, decrease the opacity so that you can see the inside view also. Then take the glyph, and on the scale also you should take the velocity, and then reset the scale factor, then apply. So you will see these velocity vectors. Okay, so that is for the time step 0. If you increase it, the time step, so the melting will start and the liquid metal will start flowing. And the inside also, you can see the Marangoni effect. Due to Marangoni induced effect, the fluid is also getting affected and its velocity also getting affected and the momentum is transferred. And what is the Marangoni effect? Actually, the the metal which is from where the melting started will get started solidify and its surface tension will start getting increased, and that will be higher as compared to the metal that is getting currently melted. So that will pull it and that will create a Marangoni stress, and then uh, that will further create the movement. And now we will see the density build. So select the macro scale dot form there. After selecting the macro scale dot form, select the slide and then take the Y normal and deselect the show plane and then put it in the plus Y direction, and from there select the variable rho, that is the density, and after that you can change the color also for better visualization. So you can select the rainbow desaturated, apply, axis grid also can be on. So let's start from the zero time step, and you will see that how the density is changing and it's moving over the interface. So red means higher density, and uh, in the blue color it means the lower density, which is basically vapor. Okay. So we can see the probe also. We can set the probe anywhere in the desired location, and with that probe we can see the temperature or any parameter that you want to see how it is varying over the period of time or over the substrate distance. So after that, select on the quartile chart view, and there uh, go into the load selection over the time, and from here all the parameters are given. So just select the first, select all, and then deselect all, and then select the temperature. So you will see that this is how the temperature is changing. So on the x-axis it's the substrate distance, on the y-axis it's the temperature. Okay. So all of these views we have plotted, and this is also like they are just many images at different times that has been put together. So this is the Marangoni flow, and this is the cross section. Okay. So this is all for now, and now in the next session, Dr. Abardeep will be there. We'll take the session on microstructure,